Hello, today we are going to talk about titration. Titration is the method to analyze the concentration of one compound based on the concentration of another compound. We can define it as the quantitative analytical method used to determine the concentration of an unknown solution by reacting it with a standard solution of known concentration. Here we can see that during the titration, we have titrant. We can call it analyte more appropriately, and it is the solution of unknown concentration, and we can include an indicator, and the compound that is used to define the concentration of titrant is called titrant, as shown here. And based on the reaction, and we can observe some kind of changes like colorimetric changes, color changes, or precipitate in the solution. So this kind of phenomena help us to define the concentration of one compound based on the concentration of another compound, and the process again is called titration. So the another important point we have to pay our attention to is the end point, in which indicate the color changes or the intensity of the precipitate remain constant. In different types of titration, we can use either color changes or precipitate. Okay, the basic principle of titration is stoichiometry, balanced chemical equations, mole concept, as shown here in an example of a reaction between hydrochloric acid and sodium hydroxide, forming sodium chloride, which is ionized, plus water in equivalence point, mass volume multiplied expression equals the concentration mass volume multiplication after reaction. So this is about stoichiometry relationship. Stoichiometry relationship is between the relative quantities of substance taking part in a reaction forming a compound, typically a ratio of both integers. In this example, taking place between iron 3 oxide and carbon, forming iron plus carbon dioxide. And here we can see stoichiometric calculations in a ratio 2 to 3 and 4 to 3 after the reaction. And before entering into the topic of titration, we need to appropriately understand the concentrations. There are various types of concentrations. Here I deal with 5 of them: mass percent concentration, volume percent concentration, molarity, normality, and molality. The mass percent concentration is the one that is defined as the percent by mass, which equals mass of solid divided by mass of solution multiplied by 100%. And in volume percent concentration, we express it as the volume of the solid divided by volume of solution multiplied by 100%. In research papers, we can often see the concentration 10%, for example, and in brackets m dash, m over m, or v over v, or m over v. So those m stands for mass percent and v stands for volume percent. So this kind of calculations are used for m over m or v over V concentrations. And the one that is used in titration is molarity or normality, which differ by the number of moles or gram equivalents of the solid. So the molar concentration is the number of molar concentration stands for the number of moles of solid in 1000 milliliter of solution, and in normality that is equal to the gram equivalence of solid in 1000 milliliter of solution. For molarity, we use mole over liter, and in normality we use gram or gram equivalence over liter. And there is another concentration termed molality, and the molality equals number of moles of solid in 1000 gram of solvent. Here in these two concentrations we use solutions, and the molality is the number of moles in 1000 gram of the solvent. So the unit for molality is mole over kg. Okay, we'd better to keep in mind the prefixes like tera, giga, mega, kilo, hecto, deca, which are used in different calculations, and this may not be used much, but we'd better to keep in mind these prefixes. Deca stands for 10. So if we have 10 to the power of 1, okay, which 1 is usually not written, so it equals 10. If we have 10 to the power of 2, which means after 1 there are 2 zeros, which means, okay, 100. If we have 10 to the power of 3, so it equals to 1000, which means there are 3 zeros after 1. And vice versa, if we have 10 to the power of minus 2, so it means before 1 there are 2 zeros, or if we have 10 to the power of minus 4, it means we have 4 zeros before 1. So these are the things we have to keep in mind. We have to keep in mind that deci stands for 10 to the power of minus 1, centi stands for 10 to the power of minus 2, milli stands for 10 to the power of minus 3, and from milli, micro, nano, and pico, every time we add a minus 3. So micro mole, for example, stands for the mole to the power of minus 6, nanomole stands to the power of minus 9, or picomole stands for 10 to the power of minus 12. And here we can see the similar tendency, deca, hecto, and kilo, and between kilo and mega there are 3 zero differences between mega and giga, another addition of 3 zeros, and tetra, this is tetra, I'm sorry, it's not tera. I'm sorry, tera, this is true, sorry, terabyte, yeah. And from the information, from the volume of the information we know, kilobyte, megabyte, gigabyte, terabyte. So this can be easily kept in mind, but we'd better to keep in mind this as well: milli, micro, nano, and pico. Okay, and here we can see these prefixes in other example from tera, okay, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, nano, and pico. Okay. And the first type of titration we are going to talk, this is the largest volume of the topic. This is acid-base titration. Acid-base titration based on neutralization reaction. The examples can be the reaction between strong acid and strong base, or weak acid and weak base. And in this type of titration, we can use different indicators, having some color changes in some ranges of pH. From school lessons, we know about phenolphthalein, methyl orange. There are many types of indicators, and today we can use a universal indicator, which has a wide range of color change. In pharmaceutical applications, we can use acid-base titration for the quantification of aspirin, for example. It can also be used for determination of acidity and alkalinity. And in order to understand the essence of acid-base titration, we need to understand the definitions, the definitions of acids and bases. Today, we understand acids and bases from different angles, but there are actually three different theories about the definition of acids and bases: Arrhenius approach, Bronsted-Lowry approach, and Lewis approach. The Arrhenius theory includes the production of hydrogen ions in water, and the bases are considered those compounds producing OH ions in water, which means the inclusion of water is a kind of necessity in this condition. I mean, for example, hydrochloric acid is an acid in water. If we talk about hydrogen chloride as in gaseous state, okay, we cannot claim it as acid. Acids are the ones, according to Arrhenius, that produce the hydrogen ions, and bases are those that produce hydroxide ions in water. And according to Bronsted-Lowry theory, acids are those that produce proton donor. Okay, actually, here we can claim that they stand for the same meaning. But for the basis, it can be a bit different. So according to Bronsted-Lowry theory, bases are those that accept protons. So the bases are proton acceptors. And according to Lewis definitions, acids are the ones that are electron acceptors, and bases are those that are considered to be electron donors. I'm not going to talk about them. If you search online, you can find out some examples. Since today we have much information, we are going to talk about these definitions. Or in general, we have to keep in mind that there are three different definitions for acids and bases. And now we are going to see some examples to acid and base. I mean, strong and weak acid and bases. Hydrogen chloride, for example, is a strong acid. Acetic acid is a weak acid. Sodium hydroxide is a strong base, and ammonia is a weak base. And according to ionization acids and bases in water, we can claim that a strong acid is the one that is ionized completely in aqueous solution by losing one proton. But I would suggest that this is not something strict. Okay, we can expect kind of high concentrations of hydrogens or hydroxide ions that determine the strengths of acids and bases. And on the other hand, there are diprotic acids, polyprotic acids. So there are some points that we have to pay some more attention. And now, the point that we can find out, we can determine the strength of acids and bases as strong or weak comes from, let's say, their dissociation constant. Now we are going to come back to the previous page. For example, we have one acid. This is dissociation constant. This is dissociation constant. When we have some acid which is ionized and ionized, let's say completely, and the concentration of the ions after multiplications and division to the concentration, to the first concentration is high. So this is going to be a kind of a strong acid. Here we can see that dissociation constant is getting high as we go to strong acid from weak acid. And the similar things can be considered for bases. I mean, okay, so this is about the acid. We are talking about pKa, and pKa is the one. Now we are coming to the previous page. pKa is the value which is the negative base minus 10 logarithm of the acid dissociation constant. So here, as we see, the dissociation constant positive is becoming negative integer, and the strong acids, as we see here, should have smaller pKa unit. Let's read now this text and we can understand more. The lower the pKa value, the stronger the acid. The lower the pKa value, as I just explained it, the stronger the acid. For example, the pKa of acetic acid is 4.8, while the pKa of lactic acid is 3.8. Using the pKa values, one can see lactic acid is a stronger acid than acetic one. The reason pKa is used is because it describes acid dissociation using small decimal numbers. The same type of information may be obtained from pKa values, but they are typically extremely small numbers given in scientific notation that are hard for most people to understand. Therefore, okay, minus 10th logarithms are used to talk about the dissociation constant. So the pKa value is one method used to indicate the strength of an acid. The pKa is the negative logarithm of the acid dissociation constant, and a lower pKa value indicates a strong acid. That is, the lower value indicates the acid more fully dissociates in water. Here we can see some more examples. These are the list of strong acids: high hydroiodic acid with pKa value minus 9.3, hydrobromic acid minus 8.7, perchloric acid with pKa equaling minus 8, hydrochloric acid, the pKa of which equals to minus 6.3, sulfuric acid minus 3, toluene sulfonic acid minus 2.8, nitric acid 1.4, chloric acid equals 1. So these are the pointers that determines the strength of acids. A strong acid is one that is completely dissociated or ionized in an aqueous solution. It's a chemical species with a high capacity to lose one proton. To lose a proton in water, a strong acid loses one proton, which is captured by water to form hydronium ion. The point that I would like to highlight is that when we talk about the strength of acids, if they are diprotic acid, we mean the first dissociation only, not the second or the third protonization. Okay, this is about the formation of hydronium ions when the proton is released from the acid. So in the solution, we can expect the formation of hydronium ion plus negatively charged acid molecule. So diprotic and polyprotic acids may lose more than one proton, but the strong acid pKa value and reaction effect only to the loss of the first proton. Strong acids have a small logarithm constant and a large acid dissociation constant. Okay, we talked already about this. And next page. Here we can see about acid and base. Acids are those that have the pH less than 7, and the bases have the pH condition with the unit higher than 7. And acids turn litmus paper red, bases turn litmus paper blue, as shown here. Acids have sour taste, or we can call acidic taste. The name came from acidic, and the taste of bases is a kind of bitter or soapy, because soap makes also a kind of basic condition. And acid feel irritating and corrosive, and the bases feel slippery. And acids include fruit juices, soda, and coffee, and bases can include baking soda, ammonia, and soap. So these are about the acids and bases and their differences. And when we have the reaction between strong acid and strong base, so we can expect the formation of salt and water, and the pH is expected not to change as shown in this example, because sodium chloride can be dissociated into ions, and they are expected not to be reassociated with hydrogen or hydroxide ions. And here we can find out about some differences between strong acids and weak acids. Strong acids are expected to completely dissociate into their ions when they are dissolved in water, and weak acids are ionized partially. And strong acids have a lower pH, let's say lower than 3, and weak acids have a pH higher compared to those resulted by strong acids, and the pH in weak acids can be higher than 4, let's say. Strong acids, dissociation constant is higher value, and this is dissociation constant of weak acids is a smaller value. And as we talked here, strong acids release hydrogens in high concentrations, which can be claimed completely, but we do not expect this kind of release from weak acids. Okay, next. And here we can see what kind of changes can be observed when we titrate acids by using bases. And here we have 4 different conditions. In the first one, strong acid is titrated by using strong base, and in this one, weak acid is titrated by using weak base. Strong acid is titrated by using weak base, and here weak acid is titrated by using strong base. So what is the difference among them? As shown here, okay, strong acids, as shown in these 2 conditions, can make their pH lower than 2, which can reach 1. And as we titrate strong acids with strong base here until, let's say, some level reaching to 2, and from 2 to 3, here we can see the kind of linear changes in the pH value. And as we reach here, we can observe kind of skip in the pH level. So while we are titrating strong acid with strong bases until we reach 3, okay, we can add some concentration. And as we add 3, for example, or 2.5, we need to be very careful. I mean, starting from 2.3, 2.5, we need to add concentration of strong bases 4 or 5 times, maybe 10 times smaller doses compared to this, so that we can be able to define the pH change. I mean, we can control the pH change, so we need to be very much careful. Which means between 3 and 10, the pH can change by the small concentration of acids or bases that could be a bit higher compared to their counter bases. And this is the example between the titration. This is an example of a titration between weak acid and weak base. As you see here, the weak acids might form the pH around 4. So when we add, as we add the weak base, so the linear change, kind of linear change can be observed until pH 7. And then here we can see the linear change. So between weak acid and weak bases, we may not observe this kind of skips as can be observed between strong acid and strong bases. So these are the pointers that we have to take into consideration while we are titrating the examples. And here we have an example between strong acid and weak base. An example can be sodium hydroxide and acetic acid, for example, and linear change as we observed here can be until 2.5 or 3, and then until 7.5. Here we can see some jumps in the pH value as we add even a weak base. So again, until we reach here, as we reach here, we need to start adding the concentration of weak bases for 5, maybe 10 times smaller doses. So then it will be possible to control the pH. And this is an example, the reverse of this one, that can happen between weak acid and strong base. An example can be kind of, let's say, copper hydroxide and hydrochloric acid. So linear change can be observed until 7, as shown here. But as we reach, let's say, 6.5, here we can observe the jump between 6.5 and 10, since we are adding a strong base, and like I'm sorry, strong base. I said hydrochloric acid. I apologize. Yeah, I didn't give an appropriate example. Here, the example, for example, can be like acetic acid plus weak acid plus sodium chloride, sodium hydroxide. So since sodium hydroxide is a strong base, so here we can see the jumping pH value by the addition of small concentration of strong base. So we need to take these things into consideration. Here we can see some examples to strong acids and weak acids. Hydrochloric acid, perchloric acid, hydrobromic acid, nitric acid, sulfuric acid, hydroiodic acids are the examples to strong acids. And nitrous acid, formic acid, acetic acid, hydrocyanic acid, hydrogen sulfide, hydrosulfuric acid, hydrofluoric acids are the examples to weak acids. And sodium hydroxide, lithium hydroxide, potassium hydroxide, barium, calcium, strontium hydroxides are the examples to strong bases. We know these metals as alkaline metals and alkaline earth metals, which means that alkali are the strong types of bases that are ionized completely. So this can be a kind of linkage between the strong bases and alkali. Okay, and the weak acids can be as ammonia, ethylamine, pyridine, alanine, amine, ammonium hydroxide, and these are the examples to weak bases. Sorry, did I say acids again? These are the examples to weak bases. And I apologize. And these are the examples, the same examples, the same trends, just as we talked. And here we can see some more examples to strong acids and to weak acids, as shown here. Phosphoric acid, for example, is a weak acid. Nitrous acid is a weak acid. Hydrochloric acid is a weak acid. And I would like to highlight that hydrochloric, hydrobromic, and hydroiodic acids are strong acids, but not hydrofluoric acid. The reason is the electronegativity level of fluorine is higher compared to water. So the strength of water to ionize hydrofluoric acid is not very high because of higher electronegativity level of fluorine. So these are the information we need to take into consideration. Okay, we talked about this earlier. This is for acids and this is for bases. And this is an example we just talked when we uh, carry out titration of strong acids by using a strong base like sodium chloride. So we can observe these kind of changes. Okay, first linear changes and then jumping point of pH between, let's say, 3 and 10, and then again linear changes. And like that, okay, when we titrate strong base by using strong acid like hydrochloric acid, so until let's say 11, we can expect some changes, linear changes, and then okay, high change now going down to 3 to pH 3 because of the strength of acid. So little concentration might cause big changes in the pH value, and then linear changes is observed again. So these are the points that we have to take into consideration while we are carrying out some titrations. Okay, and again, the differences between weak acids and strong acids titration by using any kind of bases. Here, the example is strong base. The difference is that until 7, we can observe linear change of weak acid, and until 3 pH, we can observe a linear change of strong acid, and then the jumping point of the pH value, and the reverse results can be observed between the titration of strong base and weak base when titrated with the strong acid like hydrogen chloride. I mean hydrochloric acid. Okay, hydrogen chloride stands for the gas, hydrogen and chloride, consisting of hydrogen and chloride, and hydrochloric acid is the solution of hydrogen chloride in water. Okay, and how can we know about the changes of pH if we do not use pH meters, as we were talking here in these examples? So in those conditions, when we do not use some pH meters, we can use indicators like phenolphthalein, methyl orange, and some other examples. And here we can see the ranges of different indicators. Phenolphthalein, as shown here, for example, can determine the changes between 10.2, let's say, I'm sorry, phenolphthalein, okay, between 8.2 until, let's say, 10. Yeah, and here we can see similar changes. This is actually 7.2, I'm sorry, yeah. Okay. And here we can see between 7. This phenolphthalein 7.5 until 10. Or in the example of methyl orange here, we can see the changes between 4.5 until 3.2 can be determined. So when the color intensity starts not to change, starting, for example, from 3.2 in an example of methyl orange, so we can make a conclusion that we reached the ending point in the example. Or if we are titrating from acidic to basic, when we reach this kind of yellow, which is not changing anymore, so at that dropped point, we can find out that we reached the point around 4.5. Or in an example of phenolphthalein, when we reach this kind of color, okay, different colors were used here by the intensity. As we reach this kind of color that starts not to change anymore, so we can make a conclusion that we could reach pH 10. And today, the mixtures of different indicators are used in these intentions, which is called universal indicator, that is used in laboratory condition to titrate or just to know the pH value of different solutions. So this is about the indicators that are used in titrations. And this is about the redox titration. Redox titration is the second type of titration. It's based on oxidation and reduction reactions. The examples can include the titration of potassium permanganate, or iodine, which is termed iodometry. The application can be the determination of vitamin C or iron content analysis. Here we can see the example of potassium manganate that could be used to determine the changes of some reducing agents like iron +2. So when we have this kind of color, so then we can make a conclusion that we reach the end point. I mean, the color of potassium permanganate looks like this, and the color of the solution might look like this. The acidic condition that contains iron 2 oxide. So when we add this, okay, the color starts changing from this to this intensity. So when we reach this kind of color, so we can make a conclusion that we reached some permanent color change. So based on this kind of color changes, and we can make a conclusion about the titration, based on redox reactions. So what is redox reaction? Redox titration is the same as an acid-base titration, except it involves redox reactions and generally does not require an indicator. Reagents are chosen so that the reaction is spontaneous, and one of the half reactions has a natural color change. So here is one example. As I said, permanganate ion plays the role of oxidizing agent, and this is a reducing agent. It is losing one more electron and becoming iron +3 from iron +2, and central atom of permanganate with the oxidation number that equals to -7 in this condition is having 5 electrons and becoming +2 ion. So here we can see a redox in an example of permanganate ion and iron +2 iron +2 ions. So this is an example to redox titrations. And here we have two more examples to redox titrations, including the dichromate iron to ions as shown here. Similar changes are expected to be observed here. Here, the permanganate ion playing the role of oxidizing agent, and here the oxidizing agent is chromate ion. The oxidation state of central chromium is changing from +2 to +3, so it's getting 2 electrons, and based on that, we can balance the reaction. 6 is coming from 3, 2, 3 multiplied by 2. So these are the points that we can use while balancing the reaction. Balancing the reaction is an important point to find out what stoichiometric ratios can be calculated, and this is used to calculate the concentrations of being titrated ion. Okay, and iodine thiosulfate titration is another example to redox titration. So as I said, the point we have to take into consideration is the ratio between oxidizing and reducing agents, as shown here, 1 to 5 in this example, and 1 to 6 in this example, or 1 to 2 in this example. Okay, this is about the redox reaction, redox titration. Here I provided one example. If you want to learn how to calculate the being titrated compound's concentration based on the concentration standard compound concentration, so you can try to understand this explanation by stopping the video. I'm not going to provide full explanation since we have not much time. Okay, next. This is about redox titration. Redox titration, this is about redox titration. We as acid-base titration. Acid-base titration uses different species involving different acids and bases, and redox titrations use different compounds, the oxidation state of which change. In acid-base titration, the species take part in a neutralization reaction forming water molecules, and in redox reactions, the species react through oxidation and reduction reactions. Again, their oxidation states changes. And in acid-base reactions, weak acids and weak bases are used as indicators for acid-base titrations, and in some redox species act as self-indicators, and for most cases, special redox indicators are used. And acid-base titrations are more common, and it can take place between any form of acid and base. The redox titrations are commonly seen among the D block elements. As we saw now in other examples, like manganese or chromium. Okay, iodine is a P element, and that's why it is said in here commonly seen, not in all cases. Okay, and now this is about the redox and acid-base reactions. A few more differences can be linked with the transfer of electrons in redox reactions, as we saw in iron +2 to iron -2, which is releasing one more electron. And acid-base reactions is around the transfer of protons. So this is another main difference between redox reactions and acid-base reactions. And examples here can be rusting of iron and combustion of hydrocarbons. And the examples here can be neutralization of hydrochloric acid with sodium hydroxide, forming sodium chloride and water, or the reaction of vinegar with baking soda. Okay, and another type of titration is complexometric titration. It is based on complex formation. Most common titrant is EDTA, ethylene diamine tetraacetic acid, and the application can be used for determination of calcium or magnesium ions that are used to determine the water hardness, for example, or to determine the concentration of different metals, like metal impurities in different drugs. So complexometric titration is defined as a method that involves the use of ligands to bind various metals of interest in order to determine their concentrations in solutions. This technique often utilizes chelating agents such as ethylene diamine tetraacetic acid, as I said, to form undissociated complex with transitional metals during the titration process. Okay, the utilization of EDTA can be used for transitional metals and for alkaline earth metals as well. Okay, here is one example. This is the structure of EDTA, ethylene diamine tetraacetic acid, ethylene diamine tetraacetic acid, ethylene diamine here, and tetraacetic acid. Complexometric titration are used mainly to determine metal ions by use of complex forming reaction, again, as I said. And although many complexing agents like cyanide, thiocyanate, fluoride, 1,2-diaminoethane can be used for this purpose in practice, the titrants are almost always compounds having the imino-diacetic acid functional groups. The most widely applied are ethylene diamine tetraacetic acid and H for halides can be, and the hydrate of sodium salt, as shown here. Here we can, I'm sorry, this is not halide, this can be H4Y compounds. I apologize for misinterpretation. And here we can have one example. The complex of EDTA with lead, plumbum, can react with hydrogen indigo in a blue-colored compound. So we can observe the change like this, and the ending point can be determined with this color belonging to hydroxide. Okay, that is about the complexometric titration or titration. And the last one is precipitation titration. This is the most, let's say, classical, the most ancient approach of titration based on precipitation reactions. From the school lessons, we already know about the precipitators of halides like bromine chloride ions or fluoride ions forming with the argentum nitrate, silver nitrate. Yeah, this is a reaction in which the analyte and titrant form an insoluble precipitate, as shown here, and the process is called precipitation titration. Okay, one of the earliest precipitation titrations includes the analysis of carbonate ions so potassium carbonate and potassium sulfate in potash by using, for example, potassium hydroxide. This method was invented in 18th century, and calcium nitrate is another titrant forming a precipitate with carbonic ions or sulfate ions. So calcium nitrate is used to determine the concentrations of carbonates or sulfates. And the titration's endpoint was signaled by noting when the addition of titrant ceased to generate additional precipitate. This is the point that we have to pay our attention while we are carrying out titration based on the precipitation. As we add some more concentrations of titrant, the formation of precipitate may stop. I mean, the intensity of the formation of precipitate might stop. So we can consider that stopping point of the formation of more precipitate as the ending point of titration. So that can be used as the ending point of titration in precipitation titration method. The importance of precipitation titrimetry as an analytical method reached its zenith in the 19th century when several methods were developed for determining silver ions and halide ions. And here we can see the concentration changes of chloride ions. So we can add some concentration of argentine nitrate, silver nitrate. As we reach some concentration, this is about the concentration, it's not pH value. Concentration, chloride ion concentrations, base 10 minus logarithm. So here, as we witnessed the jumps in the pH value of acid-base, strong acid and strong base reactions, here we can see this kind of jump in the precipitate concentration. So as we add some concentrations, we need to be careful to determine. As we witness the formation of kind of vague solution in that solution we are working with, so we need to reduce the volume of the standard solution to the titrated solution. So then we can reach that ending point more slowly in order to reduce the error level in our experiment. So this is about the titration, let's say, changes of hydrogen, silver chloride. And here are given the examples of chloride ions, the colors of chloride ion precipitates with silver. Silver chloride is a white colored precipitate. Silver bromide is a cream color like a precipitate, and silver iodide is a yellow color precipitate, as shown here. When we add ammonia solution to silver chloride precipitate holding solution. So then it starts to dilute. It dissolves. The diluted ammonia solution dissolves silver chloride solution. When we add concentrated ammonia to silver bromide, so we can observe the solution of this precipitate as well. And in iodide, silver iodide precipitate, we do not see any kind of changes. And in this case, okay, the solution turns purple as we add ammonia solution. And in the example of silver bromide, as we add ammonia solution, the solution turns green. So based on these kind of changes, we can find out about the changes between chloride, bromide, or iodide ions qualitatively. These are the examples about the titration. Again, there are actually 4 different types of titrations: acid-base titrations, redox titrations, and complexometric titrations. And the last one is precipitate titrations. In the first 3 ones, okay, we can use different color changes to define the ending point, or in redox, in some cases, we may not even use to define the ending point if the one of the compounds have their own special color that is changed as redox reaction happens. But in the last one, in this case, in precipitate titration, we witness the formation of precipitate, which might differ from 3 others by the formation of precipitate. So these are all that I wanted to share with you. I hope you will support us with your likes. And if you like the lecture, please support us with your likes, so then we can reach a wider audience. That's all. Thank you for your attention. Bye-bye.